Assalamu alaikum. In this lecture, we are going to talk about the electrical parameters of the transmission line. And there are four electrical parameters by which we model a particular conductor. The first one is resistance, then we have conductance, then inductance, and lastly the capacitance. So in this lecture, we will be talking about resistance and conductance. So conductance is actually the inverse of resistance, and it tells you about the ease of flow of current or electrons. And usually it is existing between the conductors, between the two phases, or between the conductors and insulators. But usually when we are modeling the transmission line, the conductance is neglected. And the question is why it is neglected. We know that the formula of conductance is I over V. As the formula of resistance is V over I, it is actually the inverse of resistance. So the formula of conductance is I over V. The current that is passing through the conductance is very small in comparison to the power that is being delivered by the transmission line. And we also know that the voltage at which the power is being transmitted through the transmission line is very high. So this current is small, that is in the numerator, and the voltage is large, which is in the denominator. The conductance value is very small. So we can easily model a transmission line without a conductance. Conductance. So that's why we don't use conductance in any of the transmission line models. We have three different type of models for short transmission lines, long transmission line, and medium transmission line. We have three different type of transmission lines, and in all these transmission line we are going to neglect the conductance. So this is for the conductance. Now if we are moving on towards the resistance, resistance is actually the element that tells you about the opposition that is being given to the current during the flow through the conductor, right? And if we are talking about the DC resistance, for DC resistance RDC is equal to rho L over A, where rho is the resistivity, L is the length of the line, and A is the cross sectional area. And usually we measure rho, the resistivity, in ohm per meter. But when we come towards the AC transmission lines, we are not using the RDC formula. We are actually calculating the R effective. And R effective is calculated by using the power loss of the conductor divided by the effective current value, which is actually the RMS value. And why we are using the R effective value? Because of the skin effect. And if I have to define the skin effect, it is actually the tendency of current to flow over the surface of the conductor when we have an AC current. So if we have a AC current that is flowing through the conductor, as the frequency increases, the current tends to flow over the surface of the conductor. Like this is your conductor. So current will, that larger density of the current will be flowing over the surface of the conductor, and the density in the center of the conductor is very small. So as the frequency increases, the skin effect increases. So if it is flowing over the surface of the conductor, then the effective resistance will be increased, and if effective resistance is increased, the I square R losses will be increased. So in order to measure the effective resistance, you have to calculate the power loss of the conductor, and then you have to divide it by I square R. Now I square the current, the effective value of current squared, and that is actually the RMS value of the current. So normally resistivity is measured in ohms per meter. Length is measured in meters, and cross sectional area is measured in meter square. But if you are using the units that are being used in United States of America, then the length will be measured in feet, area will be measured in circular mils, and it is written as C mils, and resistivity is measured in ohm circular mils per foot, and 1 mil is actually equal to 10 raised to minus 3 inches. So these are the units that are used in USA. Now there is another effect that has to be studied in case of measuring resistance: the resistance relationship with temperature. And we know that the resistance increases linearly with temperature. So for example, we have resistance R1 and there is resistance R2. The temperature is T1 when we have a resistance R1, and the temperature is T2 when the resistance is R2. So resistance actually varies linearly with temperature. And if I have to write a formula for that, R2 over R1 is equal to T0 plus T2 over T0 plus T1. So T2 is the temperature at which we have the resistance of the conductor equal to R2, and T1 is the temperature for resistance R1. Now this T0, this is actually the y-intercept. So if we extend this line, there is a point at which this line will intersect the y-axis, and this particular point is the T0. So T0 is actually then a conductor specific value. T0 is dependent on conductor. For example, we have annealed copper. The T0 value for annealed copper is 234.5, and if we have hard drawn copper, the value for hard drawn copper, the T0 value is 241. So this T0, which is actually the y-intercept of this linear graph, is actually dependent on the conductor, type of conductor, and it varies with each conductor. So this is the today's lecture on conductance and resistance, which are the two parameters, electrical parameters, that are used for the modeling of transmission line. Thank you.